Hello, my curious animals, and welcome back. Today we are going to be talking about orbitals. So, hopefully we recall that an orbital is the solution to the wave equation. So, in the context of an atom, that means that because an electron is both a particle and a wave, that an orbital is a place around a nucleus that is most likely to contain an electron. Now, today we're going to be focusing on two particular types of orbitals and, sort of how they interact with one another. And those are s orbitals and p orbitals. So, s orbitals are lower energy than p orbitals relative to one energy level, which you may recall we call 1s, 2s, 2p, 3s, 3p, and so on. Now, of course, you probably also know that there are d and f orbitals, but S and P orbitals, in the context of what we're going to be discussing today, valence bond theory and molecular orbital theory, S and P orbitals are what you're going to encounter most commonly in, for example, high school chemistry or undergraduate general chemistry and organic chemistry. So, if we recall, an s orbital is pretty simple. If we've got our nucleus here, an s orbital is just a sphere around the nucleus where the electron is most likely to be. And p orbitals are a bit more complex. So for each energy level, there exists one s orbital and three p orbitals. And because there can be three p orbitals, there has to be, three, not different shapes, but three different alignments on our x, y, and z axes that these orbitals can inhabit. So a p orbital, they sort of look like flower petals if you look at them from the side. And so a p orbital might look like this. We might call that the py orbital. This one we might call the px orbital. And then the pz orbital would be one coming out towards us, and then its alternate one going in away from us. And recall that for example, if we take the px orbital, one of these lobes describes the positive sign of the wave function, and the other the negative, because these are waves, right? They have a peak and a trough, so we will call this like the negative and this the positive. Okay. Now, some other important things are number one, that orbitals, each orbital can only have two electrons within it, and those electrons have to have opposite spins. One is called upspin and one is called downspin. And another property is that these orbitals can sort of combine together to bond atoms into molecules, right? So one way we can describe that is with valence bond theory. I'll go ahead and write it up here. You may also see that valence bond theory is referred to as VB, such as in textbooks or homework problems. So valence bond theory, or I'll write it over here, VB. Now, what valence bond theory says is that simply overlapping orbitals will combine to form bonds, okay? And so, for example, if we have hydrogen, we've just got our simple hydrogen here. Hydrogen just has a 1s orbital, and we have another hydrogen over here. Oh, drew that one a little funky. All right, we have another hydrogen over here, and this one also just has a 1s orbital. So valence bond theory that says that when these two hydrogen atoms get close together and their 1s shells overlap, that this is going to cause a bond. And importantly, valence bond theory says that the electron from this hydrogen and the electron from this hydrogen are going to be localized between these two nuclei. And so this sort of is the area that you're most likely to find these electrons. And valence bond theory also says that these two shells will combine to form a larger sort of bonding shell that is shaped similarly but slightly different. And so when these orbitals combine, this electron cloud is sort of egg-shaped. Okay, and so don't think of it as two spheres intersecting each other. According to valence bond theory, when these two hydrogens get close, their orbitals sort of merge like this. Now, one more thing that we want to sort of understand about valence bond theory is that in the hydrogen example, this is called a sigma bond. So when these two s orbitals combine, they form a sigma bond. And then this is another example. I've sort of simplified it here, and we'll talk a bit more about ethane later, or similar organic molecules. But just for the sake of this, I've simplified it so we're only showing the sigma bond on this ethane molecule. Now, sigma orbitals, if you were to sort of rotate this towards us and look at it from down the sort of the bonding plane, I guess you would say, sigma orbitals are cylindrically symmetrical. So when you look at it, when you are facing the bond, it will appear to be a circle. And so the same here, it will be cylindrically symmetrical about the axis of the bonds. And while that's all well and good, hydrogen is, the simplest molecule possible, right? It is just one proton, one electron. That's it. So what about a slightly more complex molecule like hydrogen fluoride, or even F2 fluoride, fluorine gas, excuse me. These are a bit more complex. It's not just hydrogen. It's not just one electron. Well, for hydrogen fluoride, of course, we have hydrogen, which just has its one s orbital, but fluorine has an s orbital as well as p orbitals. So it turns out that with fluorine's p orbital, there we go, fluorine's p orbital intersects with hydrogen's s orbital, and it makes a sort of interestingly shaped orbital, something almost part circular, part petal shaped. And so on one side, it sort of looks like this, and on the other, sort of something like that. And so this, of course, is also a sigma bond, because if we look at it down the axis of the bond, it will be cylindrically symmetrical. But this is an instance where it's not just an s orbital and an s orbital overlapping. It's, in fact, an s orbital and a p orbital. And now what about fluorine? Well, because fluorine's s shell is relatively small, closer to the nucleus compared to the p orbitals, it turns out that for fluorine, its p orbitals will intersect each other to form a sigma bond as well. And so we have this fluorine here, and it has, for example, this p orbital, and then a fluorine over here, and its p orbital, and so they overlap like this. And this one also makes sort of an interestingly shaped orbital. And it looks something almost like this. And once again, if we look down the axis of the bond, this will be cylindrically symmetrical. So this is also a sigma bond, but it is not an s and a p orbital overlapping, and it's not an s and an s orbital overlapping. It is a p and a p orbital overlapping. And that's nice, but what about when we get to more complex molecules? What about when we get to organic chemistry, when we have something that's still relatively simple, but even more complex than these, such as methane, which is 1 carbon and 4 hydrogens, where carbon has an s orbital and 3 p orbitals, and then hydrogen just has its s orbitals. So from what we've covered already, you might expect methane to have sort of these differently shaped, sort of weird orbitals, but that's not the case. When we observe methane, and recall that methane is tetrahedral in structure, it seems to have all of its bonds seem to be identical. They're identical length. The electrons tend to be in the same locations most of the time. So how do we explain that? Well, the way that valence bond theory explains it is through something called orbital hybridization, or sp hybridization. So we probably recall that, for example, if we have carbon's valence shell here, we've got 2s, and then carbon also has its 2px, 2py, and 2pz orbitals. And so carbon looks like this. If we were sort of to write out its energy level diagram, it would look something like this. But what actually seems to be the case is methane has equal energy orbitals when carbon bonds to all four hydrogens. What its energy level sort of orbital diagram will look like is actually like this. We have our s and our p orbitals hybridize into sp3 orbitals. And so all of these orbitals have one electron in them, which explains why carbon is tetravalent, why carbon is able to bond to four things, is because it has all of these sp3 hybrid orbitals have a space to share one more electron. And so these are slightly higher in energy than this 2s orbital, and they're slightly lower in energy than these 2p orbitals. And so it turns out that these sp3 orbitals, they have a shape that looks something like this. We've got sort of a smaller lobe on one side of our nucleus, and then sort of a larger and longer node on the other side of our nucleus. And this is because, recall that orbitals are wave functions, and they can have a positive or a negative sign. And so when we add the negative sign of one of our orbitals, we get a smaller lobe, and when we add two positive signs together, we get that bigger lobe. Sort of think of it as constructive and destructive interference. But we'll talk a bit more about that later. So this is what an sp3 orbital would look like. And so, of course, carbon has four because you take one s orbital and three p orbitals. The combination of atomic orbitals, you will always get the same number of orbitals that you put in. So you start off with one s and three p, four orbitals total. You will get out four sp3 orbitals total. Just as a small note, you've probably picked up on it already, but if carbon were to hybridize only two of its p orbitals, we would call that sp2 hybridized. And if carbon were to only hybridize s and one p orbital, it would be called sp hybridized. And so that exponent, that power, is just describing how many of those orbitals are hybridized. So let's actually go ahead and draw out what these sp3 hybridized orbitals would look like. So we've got our carbon right here in the center, and then we've got one of our sp3 hybridized orbitals up here, another one sort of out here, another one, we can sort of think of this one as sort of going back behind the plane of the board, and then one like this. And so this sort of explains carbon's tetravalent behavior. Why carbon makes a tetrahedral structure is because these sp3 hybridized orbitals are all going to be at roughly 109 degrees away from one another. I guess this one I probably should have drawn at a lower angle, but this is sort of what methane would look like, where we've got carbon and then our hydrogens are out here. And once again, we've got the 1s shell interacting with the sp3 hybridized orbital to form a sigma bond. And so we can actually take this a step further with a bigger molecule such as ethane, where we've got two carbons bonded to each other, right? So I won't worry about the H's right now, because we are focusing on carbons. And so this carbon's sp3 hybridized orbital and this carbon's sp3 hybridized orbital are going to overlap with each other. And so that is also going to form a sigma bond between these two carbons. And so just because, once again, if we've got the overlap, this sp3 orbital and this sp3 orbital, they sort of have a shape similar enough to this, so we can say, like, when we look down the axis of the bond, this is going to be cylindrically symmetric. So sigma bonds are great for describing single bonds between two atoms, like we just saw with methane, with the carbon and hydrogens, or with ethane, with carbon and hydrogen and itself. But what about when we get double bonds? How do we describe those? It turns out that sp hybridized orbitals don't contribute to double bonding. They only contribute to single bonding. And that's simply the nature of the way that we describe valence bond theory. It's sort of hard to explain. When you get to higher level chemistry, you'll understand that sp hybridized orbitals can sort of technically contribute to double bonding. For the sake of this, we're going to ignore that because we get to like hyperconjugation and way expanded valence shells, and that's beyond the scope of this video. Anyway, turns out that sp hybridized orbitals don't contribute to double bonds, and that's simply because our sp orbitals, the way that they're oriented and their shape, they don't allow for more than one overlap, if that makes sense. So if we have something like ethene, where we've got, two carbons and they are double bonded to each other, how do we describe this with valence bond theory? Well, we can still have one of these carbons, we can still have one of these bonds as a sigma bond, but it turns out that we can't use sp3 hybridization. We have to have sp2 hybridization and leave one unhybridized p orbital from both of these carbons, okay? And so we'll have a carbon and it's got, this sp2, this sp2 hybridized orbital, and this sp2 unhybridized orbital. But it will also have this unhybridized p orbital like so. So we can imagine sort of this one is coming towards us, this one is going away from us, this one is being in the same plane, and then these two going up and down in the same plane. Okay, so it turns out that this double bond is actually described by one, the overlap of two of these sp2 hybridized orbitals, but also the overlap of this carbon and this carbon's unhybridized p orbitals. Now, it's sort of hard to draw because I want to get the detail of these hybridized orbitals, but I also want to show how these two p orbitals bond. In real life, obviously, the nuclei are much smaller, they're much closer together, and these p orbitals are much wider so that they can overlap. But this is what we're stuck with. So we sort of just like pretend they're connected, So these unhybridized p orbitals will bond, and these will form pi orbitals. And so, whereas with sigma orbitals, if we look down the axis of bonding, we will see that it is cylindrically symmetrical. Pi orbitals, if we look at it sort of how we are now, the way that we can think about it is they have nodes in the middle. So if you are facing the orbitals head on, you'll see that there's sort of a node in the middle where there's no pi orbital. Now we can also extend this even to triple bonds. So for example, if we take something like molecular nitrogen, which has a triple bond, I'm going to try to draw this in 3D, so bear with me. We've got our nitrogens here, and I'll go ahead and just draw the sigma bond as a line. We understand that this sigma bond is sp hybridized. We've got nitrogen's lone pair here, and the bond between them, there's two sort of areas of electron density, which means that these nitrogens are going to be sp hybridized. So just one s orbital and one p orbital. So just understand that this is an sp hybridized orbital. I'm just not going to draw it because things will get a bit messy, as we'll see. Now I'll go ahead and draw nitrogen's unhybridized p orbitals above and below the plane where the bonding is occurring. And so I've drawn them more as elongated petals, but just know that, of course, they are overlapping in real life, more or less. But of course, we know that nitrogen is triple bonded, so we need one more unhybridized p orbital in order to form this triple bond. And so it turns out that this last unhybridized p orbital is going to be sort of like this. Okay, so we can think of these red unhybridized p orbitals as being above and below the nitrogen, and we can think of these green unhybridized p orbitals as being behind the board and in front of the board, right? So these p orbitals are going to bond, combine like this, and these p orbitals are going to combine like this. And there we have our triple bonded molecular nitrogen, where we've got an sp hybridized orbital and two unhybridized p orbitals, so we can form that triple bond. So next we're going to talk about molecular orbital theory, which is another way that we can describe bonding. And while valence bond theory describes bonding as the overlapping of different types of orbitals or hybridized orbitals, molecular orbital theory describes bonding as sort of a mathematical combination. So we'll call it a linear combination of atomic orbitals to form a molecular orbital. That is to say, how electrons are distributed around the entire molecule, whereas valence bond theory described how electrons are distributed around an atom and how those orbitals combine for bonding. And so once again, recall that orbitals have a positive and a negative node. And so we can do additive or subtractive combinations of these orbitals. And when we do additive combinations of atomic orbitals to get a molecular orbital, we will get a lower energy molecular orbital, which we'll call later a bonding orbital. And when we subtractively combine these atomic orbitals, we will get a higher energy, or what we'll later call an antibonding orbital. And so recall that with valence bond theory, we had, with hydrogen, for example, we had these two s orbitals overlapping, and then this would form sort of like an egg shape. And molecular orbital theory in the case of hydrogen predicts something very similar, although it's not the exact same shape. We get the combinations of these two orbitals, and we'll get sort of another elongated but if slightly rounder molecular orbital. So again, they look similar, and for these purposes, they might as well be the same, but they do describe different shapes. And now also recall that with valence bond theory, to form pi orbitals, we had these unhybridized p orbitals, which overlapped with each other to form a pi bond. Molecular orbital theory describes something a little bit different. With pi bonding in molecular orbital theory, we don't get the overlapping of p orbitals, because once again, we are adding every single atomic orbital. So in this case, this might be, we might call this ethane again. So there's some hydrogens out here that we're going to ignore for now, because in this case, it's not super important. But with molecular orbital theory, instead of having these unhybridized p orbitals that overlap, we add all of the atomic orbitals from all three of the hydrogens over here, all of the hydrogens over here, and from both of these carbons, and we get a pi bonding orbital. So it's not just a pi bond, it is a pi bonding orbital. And that looks sort of something like this. Almost like a kidney bean or like lobes of a dumbbell. And so that is what our pi bonding orbital looks like. This one we might call like a py bonding orbital. Of course, if we have it like coming out of the board, and then on the other side of the board, that would be a px bonding orbital. And then if we have it this way, it would be a pz bonding orbital. And so recall earlier I said that when we add the positive nodes, we get these bonding orbitals, but when we combine orbitals subtractively, we get anti-bonding orbitals. And so the bonding orbitals contribute to the bonding of this molecule, but these anti-bonding orbitals, when electrons inhabit these, they actually diminish from the overall bonding of the molecule. And so we'll see in a minute why certain molecules won't form naturally, sort of from a mathematical perspective, as well as from just more of a common sense perspective. But these anti-bonding orbitals look different. This is what a pi bonding orbital looks like, but a pi anti-bonding orbital is a little bit different. So once again, we've got our two main nuclei here, and these anti-bonding orbitals look sort of something like this. Okay, and so with molecular orbital theory, when we linearly combine all of these orbitals, these molecules will have both of these orbitals. It will have a pi bonding orbital and a pi anti-bonding orbital. The pi anti-bonding orbital, or a sigma anti-bonding orbital, may not necessarily be inhabited by any electrons, but the molecule has both of these available to put electrons. Now, when we talk about molecular orbital theory, it is also useful in determining something called bond order. And essentially, bond order is just how many bonds a molecule will have. And we can determine bond order using something called an orbital diagram. And so an orbital diagram looks something like this. If we take, once again, the simplest molecule, hydrogen, each one of these hydrogens will have these 1s atomic orbitals. And they can combine to form this sigma 1s bonding orbital and a sigma 1s anti-bonding orbital. And recall that when we combine these, the bonding orbitals are lower in energy, the anti-bonding orbitals are higher in energy. And so each hydrogen has one electron, and so they will combine, and they will both occupy the sigma 1s bonding orbital. And that is because, or the reason they won't occupy the sigma star or sigma 1s star anti-bonding orbital is because, of course, they're going to occupy the lowest possible energy state. And so right now, that is the sigma 1s bonding orbital. And now we can actually determine bond order from this using this sort of nifty little formula. So the formula to determine bond order is the number of bonding electrons minus the number of anti-bonding electrons, all divided by 2. So let's try it out for hydrogen. For molecular hydrogen, we've got 2 bonding electrons minus 0 anti-bonding electrons divided by 2 is going to be 1. So hydrogen has a bond order of 1, which is why hydrogen just has that single bond. So how does this work for something like oxygen, O2? Well, oxygen is the 8th element, so we will have 8 electrons total, which means we will fill our 1s, we will fill our 2s, we will half fill 2p, and then we will add one more electron into one of our 2p orbitals. And that'll be the same on both sides, of course, since diatomic oxygen. And so we can start filling these orbitals. So our sigma 1s orbital, bonding orbital is filled. Our sigma 1s star orbital is filled, because that'll be 4 total. From our 2s, both of these will be filled once again. And now from our 2p, let's count, right? So we've got 4 and 4 electrons from both. So our pi 2p orbitals will both be full, right? So there's 4 electrons. Our sigma 2p will be filled. There's 6 electrons. And then our pi 2p antibonding orbitals will each be half filled, right? So let's just double check, right? We'll have 16 electrons total. So we've got 2, 4, 6, 8, 10, 12, 14, 16. Perfect. If you were wondering, the reason that we have these 2 pi 2p orbitals and these 2 pi 2p antibonding orbitals and 1 sigma orbital is because, of course, you have 3 p orbitals, and so each p orbital can contribute to a sigma bond or to a pi bond. And so, of course, we can have 6 total, you might say, 6 from the pi bonds and sigma bonds total. And so if there can be 2 electrons in a sigma bond, that leaves 4 freed up for the pi bonds. So there's our oxygen orbital diagram. Hopefully it's clear enough. So let's go ahead and test this out, right? So oxygen is double bonded to itself. So let's see if we get a bond order of 2. So our number of bonding electrons for oxygen is 2, 4, 6, 8, and 10. So we've got 10 bonding electrons minus the number of anti-bonding electrons. We've got 2, 4, 6. So minus 6 by 2. That's 4 by 2. We get 2. Oxygen has a bond order of 2, which makes sense because oxygen double bonds. And you can try this out for pretty much any molecule. You can try it out once again for molecular nitrogen. You'll get a bond order of 3, and so on. So let's just go ahead and review and compare these 2 theories that help us describe chemical bonding. Okay, so recall for valence bond theory, electrons are localized in between atoms where their bonds, where their orbitals overlap. With molecular orbital theory, electrons are delocalized throughout the entire molecule and around the entire molecule in a molecular orbital. With valence bond theory, we can describe when something has multiple bonds with orbital hybridization. Whereas with molecular orbital theory, orbitals do not hybridize. So with valence bond theory, if we have something like methane, that is described by sp3 hybridization, whereas with molecular orbital theory, when we add all of the atomic orbitals together, we will get identical sigma orbitals for all of the hydrogens attaching to carbon. In terms of actually how the orbitals are formed, recall that in valence bond theory, the overlap between orbitals is what forms bonds, whereas in molecular orbital theory, I've shortened it here to LCAL, LCAL. Linear combinations of atomic orbitals form the bonding and anti-bonding orbitals. And finally, valence bond theory is extremely useful when we are studying something such as molecular geometry, whereas molecular orbital theory is going to be a lot more useful in certain situations, such as when we're studying or analyzing electromagnetic phenomenon. And one that comes to mind is like paramagnetism or diamagnetism. Molecular orbital theory is going to be a lot more useful in that situation, but rest assured, you're definitely going to be using both of these when you are studying chemistry. So yeah, I hope this video was helpful, and I hope it satisfied your curious animal brain. So just a reminder to stay curious, stay skeptical, and always be kind. And I'll see you next time.